Hi, all. Welcome to the second lecture on electromagnetics. This lecture also we are dealing with module 5, and the topics that will be discussed are electromagnetic wave equations from Maxwell's equations and uniform plane waves. So, talking about electromagnetic wave propagation. The first thing that we need to know is, what do you mean by a wave? So, waves are means of transporting energy or information. Hmm? And from the name electromagnetic wave, what do we understand? We understand that an electromagnetic wave is generated due to the interaction of electric and magnetic fields. So there are various different kinds of waves that come under the category of electromagnetic waves. So examples of those waves which can be categorized as electromagnetic waves are radio waves, TV signals, radar beams, and light rays. And for any electromagnetic wave, there are three fundamental characteristics that the wave must satisfy. So the first one being that the velocity of propagation, that is the velocity at which the wave travels, that is going to be very high. And any property of a general wave that will be exhibited by an electromagnetic wave. And electromagnetic waves always radiate outwards from the source. So source means the particular point or the cause that is responsible for generating the electromagnetic wave. So these are three fundamental characteristics of electromagnetic waves. So now, if a wave has to propagate, what is necessary? That is, you have a wave that is moving from one point to another point. It can move through a medium. Okay. So based on the three main parameters, okay, that is the conductivity, the permittivity, and the permeability, uh, medium can be classified as you can see in the slide. Okay, broadly, the different media through which electromagnetic waves can propagate, they are classified as free space. That is one media. And how is a free space characterized? The conductivity is zero, and since your relative permittivity and the relative permeability, epsilon or mu r both are equal to 1. So epsilon will be equal to, that is the permittivity and the permeability of the medium is purely equal to that of free space, epsilon 0 and mu 0. So that is how a free space is characterized. The next is a lossless dielectric. That is another example of another media. For a lossless dielectric, again, sigma is 0, but epsilon and mu are equated to epsilon r into epsilon naught and mu r into mu naught. And the conductivity is much less than omega epsilon. Here, the omega stands for the angular frequency of the wave. So this is how a lossless dielectric medium is characterized. The next type of medium is a lossy dielectric. Okay, so lossy dielectric is where the conductivity is not equal to 0. That means it can partly conduct. A medium that can partly conduct is normally referred to as a lossy dielectric. And that's why we are saying that sigma is not equal to 0. So it's also called, that is another name for a lossy dielectric, is an imperfect dielectric or an imperfect conductor, because it is not fully conducting and it is not fully insulating. It lies somewhere in between. Such materials are referred to as lossy dielectrics. So it is a partially conducting medium with sigma not equal to 0. Epsilon is equal to epsilon r epsilon naught, and mu is equal to mu r mu naught. And the last category is good conductors. That is, they are all perfect conductors, fully conducting. ideally speaking, your sigma tends to infinity. Okay, and for conductors, for good conductors, your epsilon is equal to epsilon naught. That means for good conductors, epsilon r is considered to be equal to 1. So epsilon is equal to epsilon naught, mu r, but in the case of mu, okay, mu r will have a value depending on the type of conductor. So mu is equal to mu r into mu naught, and the sigma, the conductivity, is much greater than omega epsilon. Okay, so this is how the different media through which electromagnetic waves can propagate is classified. Okay, so with that introductory note on electromagnetic waves, what is the electromagnetic wave and the different media through which electromagnetic waves can propagate, we're coming to the first part, which is to derive an equation. That is, we're going to derive the general wave equation for an electromagnetic wave from Maxwell's equations. Okay, so this equation, okay, that is the equation for an electromagnetic wave, which is derived from Maxwell's equation. We can actually derive this for any of the media that we just spoke about before. Okay, that is, there is a general wave equation for a lossy dielectric, for a lossless dielectric, for free space. Okay, so the case of the lossy dielectric, okay, that is normally considered to be the general case. So what we're going to do is we're going to derive the general wave equation from Maxwell's equations for a lossy dielectric. And once you know the expression for the lossy dielectric, if you give some simple substitutions, the wave equation for lossless dielectric and lossless dielectric and free space can also be obtained. So to start with, we are starting with deriving the electromagnetic wave equation from Maxwell's equation for a lossy dielectric, which is the most general case, and all other wave equations can be derived. If you know this equation, the other wave equations can be derived easily. Okay, so the first thing that you need to know is, what do you actually mean by a lossy dielectric? A medium in which an electromagnetic wave loses power as it propagates due to poor conduction. That is referred to as a lossy dielectric. So as I mentioned earlier, I just mentioned this in the previous slide also, uh, lossy dielectric is also referred to as a partially conducting medium. That is, it is sometimes called an imperfect dielectric or an imperfect conductor. Hmm. So in this case, what were the conditions? Those who have doubts, you can just refer the previous slide. Your sigma is not equal to 0. Okay, epsilon and mu are present. This is the method. Okay, so now we're going to start with the derivation. Some introductory statements are written, some of which I've already gone through with you. In general, wave equations can be obtained by relating the space and the time variations of electric and magnetic fields using the Maxwell's equations. So what do you understand from that? When you write a wave equation, it will actually relate the space and time variations. What do you mean by space variation? Space means the variation with respect to the coordinates. That is, for example, a field has how many coordinates? Say we are talking about 3D vectors. Okay, so there is some x coordinate, y coordinate, z coordinate for the electric field. Similarly, the magnetic field will also have an x coordinate, a y coordinate, and a z coordinate. Okay, so we are going to relate the space, that means the coordinate or the position of the electric field and the magnetic field, that is going to be related with the time variation. Now, why does the time concept come here? Because your wave is moving. It is moving with respect to time. That is, what does it imply? Right now, we are dealing with time varying fields. So your electric field and the magnetic field, both, along with having a position, they're also varying with respect to time. Okay, so when you relate the space and the time variations of electric and magnetic fields, you will get what you call the electromagnetic wave equation. So we are considering, that is, the lossy dielectric is described in this way. It is a linear homogeneous isotropic medium with parameters mu, epsilon, and alpha and sigma. Okay, and we are going to assume that the medium is source free. So what is the assumption here is your medium is source free. So what does it imply? When you say the medium is source free, it implies that the medium is charge free. That means that automatically implies that your rho V is going to be equal to 0. Okay, so this is an important point that you need to know about a lossy dielectric medium. It is a medium where your sigma is not equal to 0. Okay, but the medium is source free or charge free. That is, your rho V is equal to 0. So how are the Maxwell's equations given? So these are the Maxwell's equations. The four equations are given here. Del cross E. So you see equation 1 and equation 2, you should not be having any confusion at this point of time. Okay, I've been repeatedly talking about this. Del cross E is minus mu dou H by dou T. Similarly, del cross H, which is equal to J plus dou D by dou T. That is how you get equation 2, where your J obeys Ohm's law and that is the conduction current density and it is equal to sigma E. Now, since the medium is charge free, what happens? Your del dot B and del dot D both are equal to 0. So if del dot B is equal to 0, it implies that del dot H is also equal to 0. And del dot D equal to 0 also implies that del dot E is equal to 0. So these are the four that is corresponding to a lossy dielectric medium, which is a linear homogeneous isotropic medium, which is charge free. Okay, by substituting rho V equal to 0, these are the four Maxwell's equations that we get. That means the electromagnetic wave equation, these four equations form the basis for deriving the electromagnetic wave equation in a lossy dielectric medium. So now what we're going to do is to eliminate H from equation 1. What is equation 1? In the previous slide we've just written that del cross E is equal to minus mu dou H by dou T. That is your equation 1. So to eliminate H from equation 1, what we're going to do is on both sides of equation 1, we're going to apply the curl. So you know what is curl, okay? It's the cross product, del cross. So when you apply a curl on both sides of equation 1, you're going to get equation 5. Del cross E is equal to minus mu del cross dou H by dou T. So what you have to remember here is del operator. What is a del operator? Is actually the 3D differential operator, and your del operator performs the differentiation with respect to space. How can you justify that? See, what is your del? Your del operator is actually dou by dou x ax plus dou by dou y ay plus dou by dou z az. So what does that imply? The differentiation is with respect to x, y, z and so on. That means the differentiation is with respect to the space. And what does dou by dou t imply? Dou by dou t is a differentiation with respect to time. And both, so you should understand that the differentiation with respect to space or with respect to time, they are independent of each other and they can also be interchanged. Okay, so what happens is equation 5 can be written as del cross E is equal to minus mu okay, dou by dou t of del cross H. So we've just interchanged, okay? Instead of writing it as del cross dou H by dou T, we have interchanged. That is, it is actually a property of these differentiation operators. They are independent of each other and they can be used interchangeably, okay? So that is a property. You can understand it in that way. Now what happens? We know an expression for del cross H from Maxwell's equation. It is equal to minus sigma E plus dou d by dou t, where d can also be written as epsilon e. Okay, so we're going to substitute that over here. If you see in equation 6, del cross H, we're going to substitute from equation 2, which is the Maxwell's equation. And that is how you get equation 7. which is easy to follow. It's just a substitution. Okay, if you carefully look at it, there should not be any confusion. So once you substitute, you get equation 7. Now, this is a vector identity. We've used this in derivations earlier also. So, it is important to know that in these kind of derivations, whatever vector identity is mentioned, okay, the derivation of that identity is not important, but it is, if I mean, because these derivations you should be knowing. So, if you have to know the derivation, you should be knowing this identity. Okay, so if you see in the previous lecture that we derived, there was the identity for A cross B. Okay, del dot A cross B. And we had used that. So similarly, these kind of vector identities are all important and you should know those identities by heart. Okay. So here equation 8 shows you an identity. Now we know that because of the property of the medium that we're considering, since rho v is 0, the del dot E is 0. Okay, so equation 8 can be modified and can be written as equation 9. Del cross E is equal to only minus del square E. Okay, that means only only the second term remains, minus del square E. The first term becomes 0 because del dot E is equal to 0. So now the del cross E value that we got, that is, it is equal to minus del square E. We're going to substitute this into equation 7. Okay, so when you substitute into equation 7, you'll get what you call equation 10. Del square E is equal to mu sigma dou E by dou T plus mu epsilon dou square E by dou T square. So this equation is referred to as the wave equation for the electric field E. Okay, so this is the wave equation written in terms of the electric field. Similarly, the wave equation in terms of the flux density D, how can you write it if you substitute the, that is, what is the relation? D is epsilon into E. So I'm just going to multiply with an epsilon on both the sides. And then this equation will get modified as del square D is equal to mu sigma dou D by dou T plus mu epsilon dou square D by dou T square. So that is the wave equation written in terms of D. Okay, so now we got the wave equation. So in general, what you have to understand is wave equation is written in terms of E, in terms of D, similarly in terms of H and B also. That is wave equation in terms of the magnetic field and magnetic flux density. So on similar lines, okay, what we're going to do is for the second equation, that is, what was the second equation? Second Maxwell's equation. I'm referring to the second Maxwell's equation. So del square H, del cross H, okay, del cross H is equal to sigma E plus dou E by dou D by dou T, where the D can be written as epsilon into E. And for that second Maxwell's equation, like I did in the previous case, I'm going to use the curl operator on both sides. Okay, and that's how I get equation 12. When you use the curl operator on both sides of Maxwell's equation, the del cross H equation. And here again, using your operators interchangeably, you form equation 13. Del cross H is sigma del cross E plus epsilon dou by dou T of del cross E. And for del cross E, you can observe in the next slide, we'll be substituting it based on Maxwell's equations. So I hope till equation 13, the derivation is clear to all of you. So as I mentioned, we are substituting for del cross E, okay, and in equation 12. And then what do we get? We get equation 14, okay. It's just a normal substitution. There should not be any confusion in that, okay. Now, again, like we used the vector identity for E, we are using the vector identity for H. And we already know from the property of the medium that del dot H is equal to 0. So what happens? Your del cross H is equal to just minus del square H. So this value, we are again going to substitute into equation 14. And that is how you get equation 17. So this equation 17 is referred to as the electromagnetic wave equation for H. That is, your wave equation is written in terms of the magnetic field H. Okay. And for equation 17, if you substitute for H, in order to get this equation in terms of B, what can you do? B is mu into H. So multiplying with the mu on both the sides, you get the last equation that is shown on this slide. And then what happens is, in place of this mu H, you just replace it with a B, and that will give you the electromagnetic wave equation in terms of B. So here, as I mentioned, when you substitute mu H as B, the equation 18 that you get, this is referred to as the electromagnetic wave equation in terms of B. Okay. So now, what you understand, that is, we've actually derived 4 wave equations. Okay. The wave equation in terms of E, D, B and H, and these 4 equations are actually written in the form of field vector 3D equation form. This equation 19 will actually summarize. So what does this equation represent? It represents the equations, the wave equations we have now derived, the electromagnetic wave equation for which medium? It is the lossy dielectric medium, okay, which is a linear isotropic homogeneous medium, which is charge free. Your rho v is 0, sigma is not equal to 0. It has an epsilon and a mu. Okay, so why we are considering this medium first? This is the most general case. Okay, and by suitably substituting the parameters, the wave equation for the other medium can be easily obtained. So right now we have derived the electromagnetic wave equations from Maxwell's equation, okay, for the lossy dielectric medium. So now, if you want to derive the electromagnetic wave equations for a lossless medium, what is going to be, what do you have to actually change? See, if you see, for a lossless medium, it was defined with sigma equal to 0, okay, and it has an epsilon and a mu. Okay, so the main difference between a lossy and lossless medium is with regard to the sigma. For the lossy dielectric that we just derived, sigma was not equal to 0. But for a lossless medium, your sigma will be equal to 0. So what is the only difference? See, when you write your Maxwell's equations, the term involving sigma, it will be equated to 0. Just equate that term to 0. And you will get this equation. That is one way. Or in the other way, or another way to look at it is, see, if you look back into the previous slide, you have those final equations, wave equations for a lossy medium. In those equations, if you just substitute the sigma term to be equal to 0, you will be left with these two equations. So here, since actually the most important equations are wave equations in terms of E and wave equation in terms of H. D and B, those wave equations are actually derived from E and H. Okay, so these are the two wave equations in terms of electric field and magnetic field for a lossless medium, because sigma is equal to 0. So what is the only difference? When you substitute sigma is equal to 0 in the previous derivation, you will obtain these expressions. Okay, so that's why I said lossy dielectric can be considered to be the general case. And if you just make these small substitutions in those equations, the wave equations for the other media can be easily obtained. And similarly, if you want to obtain the wave equations for free space, what is the difference? For free space also, sigma is equal to 0. And in place of mu and epsilon, what happens is, for free space, epsilon r and mu r are equal to 1. So what happens? Epsilon is equal to epsilon 0 and mu is equal to mu 0. So we already know the expression for the lossless medium. In the lossless medium also, sigma was 0. In place of epsilon and mu, all you need to do is you replace it with mu 0 and epsilon 0. So sigma is equal to 0, and in place of mu and epsilon, you substitute mu 0 and epsilon 0, and your resulting equations that you get will be corresponding to the wave equations for free space. That is, these four equations represent the wave equation which is derived from Maxwell's equations for free space. Okay. So far we have derived the electromagnetic wave equations from Maxwell's equations for the different media. Okay. The next topic is about the equation to derive the equation for a uniform plane wave. So before we go on to your uniform plane wave, the first thing that we need to know is in general, what do you mean by a plane wave? Okay. So we'll study about the plane wave and we'll derive the basic expression for a plane wave. And we are actually going to see that a plane wave is a wave which propagates with the speed of light. Okay, we're going to see that, and then we'll move on to the uniform plane wave equation. So what do you mean by a plane wave? Okay, so if the phase of a wave is the same for all points on a plane surface, it is called a plane wave. This is the most simple definition of a plane wave. That is, you have a surface, okay, you have a plane surface, and you have this wave. Supposing I'm applying the wave to the input, and then this wave propagates through the plane surface, and then it leaves the plane surface. So if the phase of this wave is the same at all points, that is at the input and at the output, even after propagating through the plane surface, the wave has the same phase at all points. That is referred to as a plane wave. Okay, and adding on to this, if the amplitude is also constant in a plane wave, such plane waves are referred to as uniform plane waves. So what is a general plane wave? The phase of the wave is the same for all points on a plane surface. Okay, along with that, if the amplitude is also a constant in a plane wave, it is referred to as a uniform plane wave. So plane waves, there are three most important properties for a uniform plane wave. Okay, and they are, the first point is, at every point in space, E and H, that means what? The electric field and the magnetic field are perpendicular to each other and to the direction of travel of the wave energy. Even when we discussed lecture 1, the previous lecture on Poynting theorem, I had mentioned this point, that if supposing your electric field is in the x direction and the magnetic field is in the y direction, then the wave propagation will be along the z direction. Okay, so that is the first property. The second property is the fields vary harmonically with time and at the same frequency everywhere in space. So the field has a variation with time and with space. The frequency is the same. And the last point is each field has the same direction, magnitude, and phase at every point in any plane which is perpendicular to the direction of wave travel. Okay, it means your E and H, what it is actually implying is E and H will have the same direction, the same magnitude, and the same phase at every point, and E and H will be in a direction that is perpendicular to the direction of wave travel. Okay, so as I mentioned earlier, so see, these are the three main properties. You should be knowing this. Okay, what are the properties of a uniform plane wave? So you should be knowing these properties. Now, as I mentioned, so this 3D figure actually shows that your E is in the x direction, H is in the y direction, so the wave propagation is in the z direction. So what does that imply? Both E and H will not be having a component in the z direction. That is, your Ez and Hz is going to be equal to 0. That is, the components of E and H are always transverse to the direction of propagation of the wave. E, the component of E lies only in the x direction, not in the z direction. That means you have only Ex, there is no Ez. Similarly, you have only a Hy, there is no Hz. what is happening in the z direction? As a result of the interaction between E and H, the wave is propagating in the z direction, but directly there is no component of E along the z direction, and there is no component of H along the z direction. Components of E and H will always be transverse to the direction of propagation of the waves. So such waves are also referred to as TEM waves, transverse electromagnetic waves. So plane waves or uniform plane waves are normally also referred to as transverse electromagnetic waves. So as I mentioned, first we are going to derive an expression for a plane wave, and from there we'll focus more and also discuss about the properties and the equation for a uniform plane wave also. Okay, so the initial points have already been discussed. E is in the x direction, H is in the y direction. Okay, so that means uh, the direction of E, okay, that is the component of E is in the x direction, component of H is in the y direction. That is with respect to, that is how E and H are propagating. But then what happens? Where is your wave propagation? The wave propagation is in the z direction. That means your when you're talking about the rate of change of E, that is, supposing I'm writing dou Ex, that will change only with respect to Z. So that means dou Ex by dou Z, and similarly dou Hy by dou Z. These are the two rate of change of space terms that exists. Everything else will be zero. Okay, so that is what you mean by this sentence. Both the fields will not vary with x and y, but with z only. So what does that imply? That the change that is going to happen is dou Ex by dou Z and dou Hy by dou Z, because your wave is propagating in the z direction, and they will also change with time as the wave propagates in free space. That means for a wave equation, there is a relation with respect to rate of change in space and rate of change in time. So again, we are starting with Maxwell's equations. Okay, your del cross H is J plus dou D by dou T. Okay, and I'm going to assume that your free space is a perfect dielectric. That is the assumption. So for a perfect dielectric, what happens is the conductivity is zero. So if sigma, what is the expression for conductivity? Sigma. Is sigma zero, J will be zero. Why is J going to be zero? Because J is equal to sigma into E. Okay. So Maxwell's equation del cross H is going to be modified as equal to dou D by dou T, since J is equal to 0. So now, how can I write D? D can be written as dxax plus dyay plus dzaz in the rectangular coordinate system. Okay, and what do I actually have on the left hand side? The term is del cross H. Okay, so when you write the curl, you'll get an equation as shown in this slide. See, how do you get this equation? You know how to write the curl, isn't it? In determinant form, the first row is ax, ay, az. The second row is dou by dou x, dou by dou y, and dou by dou z. And what is the third row? hx, hy, and hz. And then you apply the kind of, your determinant, the rule, how you solve this. So when you apply the rule, you'll get this equation. Okay, that is written there in the PPT, and that is equal to the right hand side. Now H is in which direction? In the y direction, which means hx and hz are 0. Okay, so if hx and hz are 0, it automatically implies that any term, like the terms like dou hz by dou y, that is, you look at, I'm referring to the curl equation, writing curl of H on the left hand side of the equation, and then you have written the curl equation. Okay, so in this curl equation, all Hz terms and all Hx terms will be 0, because if Hx and Hz are 0, then any rate of change with hx and hz also is going to be 0. So what are you left with? The only term that remains, there are only two terms that remain. One is hy with respect to dou z, and hy with respect to dou x. Okay, and that is equal to the right hand side written in the same way. Now what happens again? See, your wave is propagating only in the z direction. So I had mentioned this at the beginning of the derivation. The only term that exists is dou hy by dou z. Okay, that is the magnetic field is changing only with respect to the wave propagation along the z direction. So dou hy by dou z is the only term that exists. There is no change in hy in the x direction. That means the term dou hy by dou x, that is equal to 0. Once again, I'll repeat this point. Your field is in the y direction, that is why a hy exists. The wave is propagating in the z direction. So if we want to consider the change, okay, that is dou hy I'm considering, I can consider it only with respect to dou z because the wave propagation is only in the z direction. There is no change in the magnetic field which happens along the y direction. So dou hy by dou x term is 0. Only the dou hy by dou z term exists. So from the equation above, only that term is written, that is equal to the right hand side. Okay. So now what happens is I'm just going to equate. So if you see, there is an ax term on the left hand side and an ax term on the right hand side. So I'm just equating that. The ay and the az terms, because there's no term on the left hand side, that will be 0. I hope you know how to equate whatever is there on the left hand side. The coefficient of ax on the left hand side is equated with the coefficient of ax on the right hand side. And that's how I get minus dou hy by dou z is equal to dou dx by dou t. And dx is written as epsilon into E. That is Ex, because electric field exists only in the x direction. So that is how I get the equation which is numbered as equation 1. Dou hy by dou z is equal to minus epsilon dou Ex by dou t. So I hope till here the derivation is clear. So now I've got a relation with respect to hy. Now I'm again starting with Maxwell's equations, which is derived from Faraday's law. That is del cross E is minus dou B by dou T. Here again for del cross E, I'm writing it in the form of a curl. I just explained how to write this in the previous slide. And that is equal to minus dou by dou t. B is written as bxax plus byay plus bzaz in the rectangular coordinate system. So now we know that the component of E is in the x direction. So like in the previous case, in this case we can say that Ey and Ez will be 0. In the previous case, since h was in the y direction, hx and hz was 0. In this case, since E is in the x direction, Ey and Ez are 0. So when you take the curl, any change with respect to Ey and Ez will be 0 because such terms don't exist. Only Ex exists. So only the dou Ex by dou Z and the dou Ex by dou Y term needs to be considered from the curl equation. Okay, and then the right hand side remains as it is. Now again we know that the component of Ex is not varying in the Y direction. The wave propagates only in the Z direction. So there is no change in the component of Ex along the Y direction. So what does that imply? Dou Ex by dou Y will be 0. Okay, so only dou Ex by dou Z exists. So only that term needs to be written. And then like in the previous case, I'm comparing the coefficients of Ay on the left hand side and the right hand side. So from that, I'll get the expression as shown. And then the B, Y in the expression, B is substituted as mu into H. Okay, so from this, I can write equation 2 dou Hy by dou T is equal to minus 1 by mu dou Ex by dou Z. So I have an equation 1 which I obtained earlier and then an equation 2 I've got now. Okay, see one thing, even though this derivation looks long, if you actually analyze it, you can understand that once you know those two Maxwell's equations and if you know the approach, like with respect to the H, with respect to the magnetic field, whatever you're doing, similarly you're doing with respect to the electric field also. Okay. So that is, instead of by hearting, try to understand the concept and please write down these equations and learn. Okay, and it will be clear. So now what we're doing is we have one equation which we have numbered as 1. Okay, just please, you may just go back to that slide and refer to that equation. When you differentiate that equation with respect to t, you're going to get this equation 3. Okay, similarly, the equation 2 that we just obtained in the previous slide, that particular equation, when you differentiate it with respect to z, you're going to get equation 4. So if you observe equations 3 and 4, the left hand side of both these equations are the same, which means I can equate the right hand side of the two equations. So equating the right hand side of equation 3 and 4, that is going to give me equation 5. Okay. Now, I hope all of you know that the velocity of light is actually given by, the 3 into 10 raised to 8 meter per second. Okay. The speed of light, that is in free space. Okay, so this v is equal to 1 by root of mu epsilon, is probably something that you've already studied in physics. So here also the 1 by mu epsilon term, okay, I can write it as v square. And if I'm considering the medium to be free space, so in free space, actually the velocity of an electron, the velocity of a plane wave, okay, is the same as the velocity of light. So I'm just rewriting equation 5 as dou square Ex by dou t square. Okay, that is equal to 1 by mu epsilon is written as v square dou square Ex by dou z square. Okay, so this equation is actually referred to as the wave equation for a plane wave. Okay, this is the wave equation for a plane wave. Similarly, so we are not going into the derivation, but just for you to know, this is one equation, dou square Ex by dou t square, that is equal to v square dou square Ex by dou z square. Similarly, we can also write dou square Hy by dou t square is equal to v square dou square Hy by dou z square. That is, in this equation 6, you just replace the Ex with Hy. That will give you the wave equation in terms of the magnetic field. Okay, so this is the wave equation for a plane wave, or the wave equation for a transverse electromagnetic wave. So this is the derivation general. This equation gives you the equation for a plane wave. Okay, there are two equations. What is written here, equation 6, is in terms of the electric field. In terms of magnetic field, what do you have to do? Just replace the Ex with Hy. Okay. So the wave equation that we just saw now, okay, dou square Ex by dou t square is equal to v square dou square Ex by dou z square. This is a differential equation of second order, and if you solve this mathematically, the solution that you're going to get, that is given by equation 7. See, these equations, that is still the wave equation, it's actually important. You should know the derivation. These set of equations that I'm going to describe in this slide and the next slide, you just need to understand. Okay, need not just by heart everything, but you need to understand. So what you have to understand is, when you solve the second order differential wave equation, you're going to get an equation that has two quantities. Okay, so here the first sinusoidal function represents the wave in the forward direction, and the second term represents the wave in the backward direction. Okay, that means your wave which is propagating in the z direction will have a positive z direction. The amplitude is Em plus, and the wave propagation in the negative z direction, it has an amplitude Em minus. So just understand that the solution of your wave equation is going to give you a sinusoidal function which consists of two components of E, where one is in the forward direction and the other is in the backward direction. And 8 is just, if you rearrange equation 7, dividing it by omega, you will get equation 8. Okay. And this equation 8 if you are going to do a partial differentiation twice, okay, with respect to z, that is, the on the left hand side I'm going to differentiate it with respect to z. Equation 8, I'm talking about equation 8. Equation 8, I'm going to do a partial differentiation with respect to z on the left hand side and with respect to t on the right hand side. Okay, with respect to z on the left hand side and with respect to t, and I'll get equation 9. Okay, so yeah, so that's how you get equation 9. When you compare the equation 6, so equation 6 is the wave equation which is expressed in terms of Ex. So when equation 6 and equation 9 are compared, okay, you're going to get an expression for the velocity. The velocity of wave propagation V is given as omega divided by beta meter per second. Okay, so beta basically it is a phase constant. Okay, we'll be talking about this a little later. And omega, as I told you, it's the angular frequency of the wave. So this equation is important. Sometimes you get problems to find the velocity of wave propagation. You may have to use this equation. Okay, so please mark that and write it down. V is omega by beta meter per second. You should be knowing that expression to solve problems. Now, like similar to how we obtained an equation for Ex as the sum of two sinusoid functions, okay, a forward and a reverse wave. Similarly, you can get an expression for Hy also. And how do you obtain it is you're using equation 2. Just scroll back to the slide, okay, to equation 2. And in that, for the value of Ex, you just substitute from equation 8. So since the equations are numbered, okay, but it's not possible for me to read out all the equations. That's why, if you have a doubt, just go back, look into that equation, and then come back and substitute and see. Okay, and then when you integrate both sides with respect to time, this is the expression. So see this, as I told you, this entire differentiation, this is not important. What you have to understand is still the wave equation. It is important. And then the velocity, the equation for the velocity V is omega by beta. This you should be knowing. And then you should also understand that both Ex and Hy can be represented as a forward wave. That is, there is a propagation in the positive direction and a propagation in the negative direction. Okay, that is what you're supposed to understand. So that's what gives you equation 11. So there are some parameters of the wave, okay, that you need to know. That is what is being described in this particular slide. So now that we have discussed about what a plane wave is, and we have derived the equation for a plane wave, and simplifying it further, we've also understood the fact that the plane wave in free space, it is where you know the values of where your epsilon r and mu r are 1, and if you substitute the value of mu 0 and epsilon 0, you get that this velocity of propagation is going to be the same as the speed of light. Okay, and the fact that both Ex and Hx is the sum of a positive propagation and a negative propagation in the positive and the negative directions. So now some constants of the wave that you need to know. Okay, the first constant is called the attenuation constant alpha. Okay, so these are some terms associated with a wave. So attenuation constant alpha, okay, that is in general when any wave propagates in the medium, there is a certain amount of attenuation. The wave gets attenuated. Okay, that is the amplitude of the signal reduces, and this is represented by a constant that is known as the attenuation constant, and the unit is a Nipper per meter. Okay, generally the unit of your attenuation constant is Nipper per meter, and for practical cases we also use, sometimes it is also expressed in decibels. So the conversion between a Nipper and a decibel is as shown. 1 Nipper is 8.686 decibel. So that is the relationship between a Nipper and a decibel. And it is also observed that when a wave propagates, okay, there is a phase change that takes place. So that so the first constant was the attenuation constant. The next constant is the change in the phase of the wave as it propagates. And that is given by your phase constant beta, which has a unit radians per meter. So that is the second constant that you need to know, the phase constant beta, which is expressed in radians per meter. Okay. See, there is one more definition of attenuation constant. Okay. Which I'm just going to dictate, and you can note it down also. Attenuation constant, sometimes it's also called as the attenuation factor of the medium. Okay, that is as the wave propagates along AZ. Okay, the direction is going to be Z, so it is along AZ. It decreases or attenuates in amplitude. So alpha, and normally the factor by which it attenuates, it is given by e raised to minus alpha z. Okay, that is how you account for the attenuation factor. As the wave propagates along AZ, it decreases or attenuates in amplitude by a factor given by e raised to minus alpha z. And alpha is called your attenuation constant or the attenuation factor of the medium. So another definition is it is a measure of the spatial rate of decay of the wave in the medium. I'll repeat it. It is a measure of the spatial rate of decay of the wave in the medium. A measure of the spatial rate of decay of the wave in the medium. And as mentioned earlier, it's measured in NEPA per meter or in decibels per meter. And the relation between NEPA and decibel is as given below. And so that is the first constant. The next constant, as I discussed, it is the phase constant. Okay. The phase constant is sometimes also referred to as the wave number. Okay. And the unit is in radians per meter. It is a measure of the phase shift per length. Okay. A measure of the phase shift per length of the wave. And these two constants, so if you see the attenuation constant and the phase constant beta together constitute a propagation constant of the medium for a uniform plane wave, and that is represented by gamma. So what is gamma? That is another constant, which is the attenuation constant, and it is defined as alpha plus j beta. Okay, the per unit length, the propagation constant per unit length is given by alpha plus j beta. So that is the propagation constant of the medium. It's a complex quantity. Now we come to eta. See, eta, intrinsic impedance. I had mentioned this term once in the previous lecture on module 1, where we were talking about the complex Poynting vector. Okay, so eta is the intrinsic impedance of the material in which the wave is traveling. That is the medium or the material in which the wave is traveling. And eta is given by the ratio of the amplitude of E to H. It could be in either direction, either both positive, because both the electric and the magnetic field has a propagation in the positive and in the negative direction. Okay, so that ratio. And the unit is in ohms. Okay, the ratio of the intrinsic impedance, the unit is in ohms. Okay, and now another thing that you know is, we know that the velocity of propagation is given by omega by beta. This was just expressed earlier. It is also, the velocity of propagation is also 1 by root mu epsilon. This was also derived earlier. Okay, so eta can also be written as the square root of mu by epsilon ohms. That is the intrinsic impedance of a medium with permeability mu and permittivity epsilon is given by equation 14. The unit of intrinsic impedance is ohms. Okay. So now that was a general expression for eta for any medium. Now supposing your medium is free space, how can you write expression for the intrinsic impedance? We know the value of mu 0 and epsilon 0. So this is a constant that you need to know. That is, if your medium is free space, the intrinsic impedance will be equal to 377 ohms. So you should be knowing this value. And the velocity of propagation is going to be the same as the velocity of light. So these two conditions holds true when your medium of propagation is free space. Okay, so the constants that we have discussed are attenuation constant, phase constant, propagation constant, intrinsic impedance. Okay, now the next constant is about the length of a wave, which is given by lambda, the wavelength lambda. It is the length of one cycle of the sinusoidal signal. Okay, so if lambda is the length of one cycle, then the signal changes phase by 360 degrees or 2 pi radians. And lambda is related with the phase shift beta, as lambda is 2 pi by beta. The unit is in meters. Okay, so that is the wavelength. And if you multiply the frequency with lambda, okay, because that is f, your velocity of propagation. Now it has got another relation as f, the frequency, into the wavelength lambda. So v has a lot of relations. V is equal to 1 by root of mu epsilon. V is equal to omega by beta. Now v is also equal to f lambda meter per second, the velocity of propagation, or it is also called as the wave velocity. Okay, so all these equations you need to know. Okay, the three expressions for v, there are three different ways in which the velocity of propagation is given: the expression for the intrinsic impedance, the expression how the expression for the wavelength, how the wavelength is related with the phase constant. Okay, so all these expressions are important, especially when you do the problem also. You will need to know these equations. You should be knowing them by heart. Okay, so far we've discussed about plane waves. What is a plane wave, the equation of a plane wave, and the various constants associated with a plane wave. Now when you talk about a uniform plane wave, okay, some things, a few things specific to uniform plane wave, that's what we're going to discuss in this section. But if you see, the derivation is more or less very similar to the derivation of a plane wave. Most of the equations are also the same, except for slight differences, because we're going to be a little more specific. So what we're doing is, so uniform plane wave. So the three main properties of a uniform plane wave has already been discussed. Okay, when I spoke about plane waves in general, the three important properties of uniform plane wave were also discussed. Okay, so please review that once. Now, if I'm considering a uniform plane wave propagating in the z direction, okay, so your E is independent of x and y. So I told you this already. If the propagation is in the z direction, dou E by dou x and dou E by dou y is going to be 0. The similar assumption or the similar fact we had considered when you just derived the wave equation for the plane wave also, okay, in the previous section. Now, when your region is source free, what does source free mean? It's charge free. So rho v is 0, del dot d is equal to 0 in that case by Gauss law. And so if del dot d is 0, del dot e is also 0. And how can you write del dot e? In Cartesian coordinate system, it's dou ex by dou x plus dou ey by dou y plus dou ez by dou z. And since E is independent of x and y, those two terms are going to be 0. So what does that imply? Dou Ez by dou z is equal to 0. This is how that equation reduces to. So this implies that your Ez is also 0. That means for a plane wave, E has no component in the direction of propagation. And similar is the case for H also. So what does it imply? E has a component only in the x direction. Okay, see, now I have been repeating this a number of times. E has a component only in the x direction. H has a component only in the y direction. There is no component of E or H in the z direction. So that has been proved also here now. Okay. So that means plane waves have only transverse E and H components. That's why EH and the wave propagation are always mutually perpendicular to each other, because there are only transverse components of E and H contribute to the wave propagation. Now, another equation is, so this is the wave equation derived from Maxwell's equation for free space. If you remember, see, del square E is equal to mu 0 epsilon 0 dou square E by dou t square. Okay, if you have forgotten, just look back into the initial portion. That is, for this lecture, at the beginning of this lecture, we had derived wave equations for electromagnetic waves from Maxwell's equation. And when we considered the free space medium, this was the equation that we derived. So from this, if I'm taking out, that is the, when you equate the LHS and the RHS, okay, and I'm considering specifically dou square Ex by dou x square, that is going to be related with mu 0 epsilon. That is, the scalar components are being taken out. So Ex, Ey, and Ez are separately considered, and those equations are written. I presume that should be self-explanatory, okay? So that's how those equations are written. For a plane wave which is propagating along the z direction, there are no variations along x and y. Okay, this we had discussed even when I spoke about the plane waves. So del cross h, okay, using the del cross h equation, okay, and considering the fact that there is no variation along x and y, that means we need to consider only the variation of the magnetic field along the z direction. Okay, so using that, you get equation 1. If you have any doubt in this equation, just look back into the derivation for the plane wave equation. There I had explained how from the curl you write down, using the curl you write the full expression, and in that all the changes with respect to x and y will be 0 because your wave is propagating only along the z direction. And then using Maxwell's equations, we can write that del cross H is equal to J plus dou D by dou T, assuming that sigma is 0. Okay. So then J, which is equal to sigma into E, J will also be a 0. Then in place of D, I'm substituting it as epsilon into E. And E is a vector. So I can write that as dou Ex by dou T Ax cap plus dou Ey by dou T Ay cap plus dou Ez by dou T Az cap. Okay. See, this is similar to the derivation of the plane wave that I just explained. Okay. Now when you equate 1 and 2 equations, the coefficients of Ax and the coefficients of Ay equated, I'll get equations as shown in the PPT. That is the equation for dou Hy by dou Z and dou Hx by dou Z. These two equations are obtained by equating the coefficients of Ax and Ay in equations 1 and 2. Similarly, to get expressions for dou Ey by dou Z and dou Ex by dou Z, I'll be using the Maxwell's equations which are derived from Faraday's law. That is del cross E is equal to minus mu 0 dou H by dou T. Okay, why? Because this is a free space. That's why mu can be substituted as mu 0. And similarly, for free space, we also know that your sigma is 0. That is why J is 0. And in place of h, I again substitute it as dou hx by dou t ax cap plus dou hy by dou t ay cap plus dou hz by dou t az cap. Again, see this del cross E, the expression, I have not expanded it here because we just discussed the same thing for plane wave. So just go back, look into how you write del cross E for a plane wave. That is using the determinant form, you write the whole expression. All the variations with respect to x and y, you just cancel it. I mean, it should be 0. That is, only the dou Ey by dou Z term and the dou Ex by dou Z term will exist. And when you compare the corresponding coefficients, this is what you will get. It is very easy. If anybody after hearing this lecture, if you have a doubt on how you got this, you can contact me personally and I'll explain it to you. Okay. Now, so that is about the relation, how the relation goes for a uniform plane wave. Now, for a uniform plane wave, we have also stated the property that E and H are mutually perpendicular to each other. So we're just going to prove how E and H can be orthogonal. For that, what I'm going to do is, I'm going to consider a linearly polarized plane wave C. Now, for our assumption, we have considered that E is in the x direction and H is in the y direction, and propagation is in the z direction. It is also possible to assume that H is in the x direction, E is in the y direction, and propagation is in the z direction. That is also correct. Okay. So for now, whatever I'm explaining, see, I have drawn a line and there are some equations. That is, there is an EY equation which is written on the left hand side of that part, the dividing line, and the EX. For now, you follow the EX equation because that is our assumption throughout. So instead of confusing you, I'll explain. with respect to that. So Ex, that is the electric field which we have assumed in the x direction. I'm writing it as E0 into a function of z minus Vt. Why z minus Vt? Because the propagation is along the z direction, and E0 stands for the maximum value of Ex. Okay. Now what I'm going to do is both the sides, LHS and RHS, I'm going to differentiate with respect to t, that is partially differentiate with respect to t, and I'm also going to multiply epsilon 0 on both the sides. So what do I get? Epsilon 0 dou Ex by dou t is equal to, what happens when you differentiate the right hand side? See, E0 is a constant. And what is the differential of f of z minus Vt with respect to t? It is going to be f dash z minus Vt into minus V. Okay, and I also mentioned that you're multiplying LHS and RHS with an epsilon naught. So everything put together, what will you get the right hand side as? Minus epsilon naught V, which is the velocity of propagation, E0 f dash z minus Vt. See, just above we have written what is this epsilon naught dou Ex by dou t equal to. Just look above. If you look above, you can find that it is equal to minus dou Hy by dou z. That is the equation. I have written 1 and 2 equated. Just below that, the first equation that I have written. The right hand side gives you the same thing, epsilon dou Ex by dou t. In this case, since it is free space, I'm going to assume it as epsilon naught. Okay. Actually, in order that you don't get confused, please do one thing. Even when you write above, like how I wrote mu naught, you please write it as epsilon naught in equation 2. Okay. Just so that you don't get confused, all of you, I'm repeating it once again. The equation 2 in this particular slide, equation 2, instead of writing it as epsilon dou E by dou t, please make it epsilon naught. When you take down the notes, you can write it as epsilon naught. So then it becomes uniform. That is, we are completely assuming only free space. Okay, so write it as epsilon naught, and mu you write it as mu naught. So then those two equations are the same. Okay. And I have written that this is equal to dou Hy by dou z. So from that, how can I find Hy? That is minus Hy is equal to, if I integrate the left hand side, I'm going to get an expression for Hy. What happens when you integrate this? I'm going to get epsilon naught V E0 f, that is f dash becomes f of z minus Vt. This E0 f of z minus Vt is equal to Ex. That is what we have assumed at the beginning. See, Ex. So what happens? Hy, how is this expression going to reduce? It becomes Hy is equal to epsilon naught V, which is the velocity of propagation, into Ex. I'll repeat, Hy is equal to epsilon naught V, which is the velocity of propagation, Ex. So from that, what do I get now? V. I know V is equal to 1 by root of mu epsilon, and since I'm assuming free space, V can be written as 1 by root of mu naught epsilon naught. So when I substitute that and simplify, I'll get Hy is equal to root of epsilon 0 by mu 0 Ex. So what does this imply? It implies that Ex by Hy, that is the ratio of electric field to the magnetic field, that is going to be equal to root of mu 0 by epsilon 0, which is 377. I had just explained about this in a couple of slides back. We spoke about this. So Ex, the ratio of the electric field divided by the magnetic field Hy, that is going to be equal to root of mu 0 by epsilon 0. If I substitute the values of mu 0 and epsilon 0, I'm going to get eta, the intrinsic impedance of free space, as equal to 377. Okay. So see, this is the conventional case that we have been assuming all along. E is in the x direction and H is in the y direction. It is, the reverse is also possible. That is, E in the y direction and H in the x direction. That is what is written. That similar derivation is written on this side in black pen. Okay, that is starting, I'm assuming Ey as E0 f of z minus Vt. On similar lines, when you derive, you will get Hx is equal to minus root of epsilon naught by mu naught Ey, which implies in this case also E by H is going to be equal to root of mu 0 by epsilon 0. So the portion that I've written in blue, okay, that is for Ex, that is what we have been conventionally assuming, that you study and you just write similarly Hx is equal to minus root of epsilon naught by mu naught Ey, because the wave can be polarized, the transverse polarizations can be in any direction. We have assumed that E is in the X and H is in the Y. The reverse is also possible. And even if it is the reverse case, the fact that eta is equal to root of mu 0 by epsilon naught, that will hold true in both the cases. Okay. Any doubt in any of these equations, you can call and ask me after listening to the lecture. So now we have derived expressions for hy in terms of ex, and similarly ex in terms of hy. Okay, so from these relations, what we can infer is that E and H at any point both are in phase and they are orthogonal. So all these things about intrinsic impedance I just discussed now, you can go through it. The unit is ohms. So now finally, how do you prove that E and H are orthogonal? See, what is the dot product equal to? E dot H is the magnitude of E into the magnitude of H into the cos of the angle between E and H. So if two vectors are orthogonal, their dot product should be 0. That is a concept that you all know. Okay. So when you take the dot product E dot H, it is, the dot product is Ex Hx plus Ey Hy, because E has the component, okay, that is E. When you write, when you're taking the dot product, you multiply with the magnitudes. Okay. So Ax dot Ax is 1, Ay dot Ay is 1, Az dot Az is 1. In the Z direction, we are not having any E or H. The E and H lies only along X and Y. Okay. So Ex Hx plus Ey Hy. That is a dot product. Now what I'm doing is, for Ex, I'm substituting in terms of eta. So the relation is eta Hy Hx. And similarly for Ey, I'm substituting in terms of Hx, written as minus eta Hx. These two equations are the ones that we just derived. Please look back into this slide and the previous slide, and you'll get to know how we are substituting. What I'm doing, I'm substituting for Ex and Ey in terms of eta and H using the intrinsic impedance relation. So what does this show? It shows that it is equal to 0. So thus we have proved that for a uniform plane wave, E and H are transverse components, they are orthogonal, and they are in phase. Okay. So with this, the concepts and the equations related with uniform plane wave is also complete. So just reviewing on what all we have discussed in this lecture, we started with the electromagnetic waves. What is an electromagnetic wave? What are the common media in which electromagnetic waves propagate? We derived the electromagnetic wave equations from Maxwell's equation. See, the most general form, general wave equation, is for the lossy dielectric case. And then we also extended it to lossless dielectrics and free space. Okay. Then we came to the case of plane waves. So we discussed what is a plane wave. We discussed particularly the properties of a uniform plane wave. We discussed the wave equations for a plane wave and found out that in free space, it has the same velocity as that of light. Okay, three different expressions for velocity I've explained. V, the velocity of propagation. Then we spoke about several constants, the attenuation constant, the propagation constant, the phase constant, the intrinsic impedance. Okay, and then particularly we spoke about uniform plane wave, and we have also proved how E and H are mutually perpendicular to each other and how eta is equal to root of mu 0 by epsilon naught. Okay, so please listen to this lecture very carefully. See, whenever you take down both this lecture and the previous lecture, please write down the notes also. Okay, and when you study also, please write down and study all these equations. Okay, I've tried my best to explain everything in detail, but when you hear this lecture at any point, if there is anything that is not clear to you or you've not understood, please feel free to either message or you can call and ask me also. So with this, those two topics, that is electromagnetic wave equations from Maxwell's equation and the uniform plane wave section in module 5 is complete. Okay. See, I'm also planning to share some interesting links with regard to polarization of light and so on. See, we have used the term polarized here when we spoke about uniform plane waves. So a couple of links, I'll share it into the Google Classroom. Okay, and you can go through it to have a better understanding of this concept physically. Okay, thank you.